welcome. Today we have an interesting question on chemical energetics. So let's say that you wanted to go on a camping trip. Beforehand, you decided, maybe I should plan for this a little bit. You realize that you're gonna need to cook some food, and for that, you're gonna need to boil some water. To do that, you need some form of fuel source. So you were wondering, what fuel source should I use? So you decided, let's try some ethanol. Maybe it'll work. Ethanol is a flammable alcohol, and it undergoes this equation right here for combustion. That is complete combustion, because it's carbon dioxide here. So using this setup right here, we can determine how effective of a fuel source ethanol is. To do so, we are going to calculate the enthalpy change of combustion of ethanol. To do that, we are going to need to burn some ethanol, make it undergo combustion, and then we needed to heat up something, which is in this case water, and we have 1,640 cubic centimeters of it. We would need to measure the temperature change, so we have a thermometer, and we have mass balance to determine how much ethanol we have used for this, and we have retort stands and clamps to just secure everything in place. After going through your experiments, you have determined that initially the burner containing ethanol was 500.0 grams. The final mass of it was 497.7 grams. Initially, the temperature of the water was 32.0 degrees Celsius, and then afterwards, the final temperature was 41.5 degrees Celsius. You also determined that the MR of ethanol, using the periodic table, you can determine it to be 46.0. So the question is, what's the enthalpy change of combustion of ethanol using all of this information? What can we do? Well, let's start with some formulas. We know that Q is equal to mc delta T. Delta T. Okay. Instead of using Q, I'm going to say the amount of heat evolved is equals to mc delta T, because this will avoid the step of Q prime is equal to negative Q, and whether or not Q is positive or negative is a bit confusing. Instead, I'm just going to write that amount of heat evolved is this, because I know that through combustion, heat is being evolved. It's exothermic. So I just need to know the amount of heat evolved. M in this case is going to be the mass of whatever I'm heating up. This is in grams. C is the specific heat capacity. In this case of water, that means how much energy do I need to give 1 cubic centimeter, actually 1 gram of water, to raise its temperature by 1 Kelvin. So this is joules per gram per Kelvin. So per gram of water, for every increase in temperature per Kelvin, I need some number of joules of energy. That's the specific heat capacity. Delta T refers to the change in temperature of whatever I'm heating up. So in this case, it's going to be in Kelvin. Let's do a little bit of cancellation. We see that Q and gram and per gram, Kelvin and per Kelvin, we have joules left. So the amount of heat evolved is in joules. Okay, that's pretty nice information. So first off, what's M again? It's the mass of what I'm heating up. I only know it's 1,640 cubic centimeters of water though. But what I do know is that 1 gram of water is the same as 1 cubic centimeter of water. So, with that information, what we can do is go over here and say that this is equal to 1640 times C times delta T. Specific heat capacity of water, that is actually going to be 4.18. Delta T, change in temperature, is going to be 41.5 minus 32.0. That is 9.5. So what is this going to give us? This is going to give us 65,124.4 joules. However, later on, when we are calculating enthalpy change of combustion, we are going to end up with kilojoules per mole. So we probably want to convert joules into kilojoules. So this is going to be 65.124 kilojoules to 5 significant figures. Okay, that's pretty nice. The next thing we need to do is to literally just figure out what is the enthalpy change of combustion. The enthalpy change of combustion is going to be negative of the amount of heat evolved divided by amount of fuel, which in this case is going to be ethanol used. Okay, we don't have the amount of ethanol yet, but what we do know is that the initial and final mass of the burner with ethanol are these. So if we take the difference of these two numbers, we can find the mass of ethanol used. Here, MR is the same as molar mass in this case, so it's going to be 46.0. This is just going to be mass over molar mass, which is going to be 2.3 divided by 46.0. This is going to give us 0.05 moles. This, as we calculated, was 65.124 kilojoules. So the whole thing is just going to be equal to negative 1302.48, which is same as to 3 significant figures, negative 1300 kilojoules per mole. Okay, does this make sense? First of all, we see that the enthalpy change of combustion is negative. Well, that makes sense because combustion is exothermic, and when the enthalpy change is negative, it means energy is being released. So yeah, it holds. Kilojoules per mole. Yes, we see that we have the units kilojoules being divided by mole, so yeah, kilojoules per mole holds out. Okay, so from all this, back to our main problem of whether ethanol is a good fuel source for this case. Well, kind of, not necessarily. There are other fuel sources with greater enthalpy changes of combustion, but for this, it's not that bad. Other than, yeah, it's just not that bad. Now, here's a little issue. According to a reference book that you found, the enthalpy change of combustion is actually going to be negative 1,370 kilojoules per mole. Then why do we calculate this value right here? And what are the 3 main reasons why the value calculated was lower? Well, let's take a look back at our setup. Here, we are having a burner containing ethanol heating up the beaker like that. But is all the heat gonna go there? I mean, if we have a burner, and then like something like that, and this is our beaker of water, not all the heat evolved is actually going to it's going to be channeled into the water. Some of it is going to be lost to the surroundings. While some, yes, it will go ahead and heat the water. So that's the main reason as to why the enthalpy change calculated was much lower. Second, let's think about this equation right here. We have ethanol undergoing combustion to give us carbon dioxide and water. In reality, sometimes it would not undergo complete combustion. So sometimes there's not enough oxygen, and so it will undergo incomplete combustion. Meaning the maximum temperature is not reached, because undergoing incomplete combustion releases less heat. As such, the maximum temperature is not reached, so like the change in temperature calculated isn't necessarily the most accurate. Lastly, back to our burner, it contains ethanol, which is a flammable alcohol, but one of the main issues with it is that it evaporates. So some of it, though not being heated, though not undergoing combustion, would also evaporate. So if you really want to know like the answer, I have it right here. So some of the heat released from combustion of ethanol that was lost to the surroundings and not transferred to the water. Combustion of ethanol was incomplete, so maximum temperature reading was inaccurate, and some ethanol might have evaporated, so mass of ethanol measured, measured, measured may be inaccurate. Yeah. Yeah, and so that's pretty much it. I hope this would help you. Thanks for watching, and I'll see you guys next time.